How about now? Can you guys hear me now? Testing, testing, uh, testing. How about now? Can you guys hear me now? Alright, awesome. Let's get started then. Sorry about the delay. This week's tutorial, we're going to be talking about, we're going to create a recursive class in Python for binary search trees. Um, First, let me just explain what a binary tree is, and then um, after that, I'll explain what a binary search tree is. So, let's take a look at a binary tree. So you can see on your screen here just an example of a of a simple binary tree. So a binary tree um, is a data structure such as this where each node represented by a circle here with the number inside. So each node has at most two children. So you can see here that node 1 has children's node 2 and node 3, and node 2 has children 4 and 5. Um, and node 4 has children 8 and 9. So you can see that if you look at this as like all of this as one tree, you can see that the left side of node 1 is a smaller subtree, and the right side of node 1 is another small subtree. And yeah, as I'm explaining things, if you have any questions, just type it in the chat. Okay, so that's what a binary tree is. Now, let's talk about a binary search tree. Alright, so now a binary search tree um, it basically builds off the binary tree data structure, but it just has some added conditions. So, for instance, um, all the values, so just like how earlier I was explaining about our our tree having subtrees. So if you look at node 8, its left subtree here has nodes containing values um, that are less than itself. So you can see here all the nodes on the left side of 8, 1, 3, 6, 4, 7, they're all less than 8. And you can see on the right side here, all the nodes on the right side of 8, 10, 14, and 13 are greater than 8. So essentially, like our binary tree data structure didn't have any such condition, whereas our binary search tree has this condition where the left side must be less than and the right side must be greater than. And other than that, um, right, so a binary, just some properties about a binary tree node. So each node contains its data. So, like for example, this node contains the number or integer value 1, and it also contains pointers to its left child and its right child. So our binary search tree um, will also use this information. And by that I mean we'll use this information when we code the class for this binary search tree. So any questions so far? Just let me know in the chat if anything's unclear about these data structures. Okay, let's go ahead and start creating our class. So we'll just call our class BST. Um, and we want it to just inherit from the object class, um, which is just a class that all um, like everything in Python inherits from this object class. So we'll just mention that here. Now let's go ahead and define the constructor. So by default, every um, object comes with its own constructor. However, we want to override the existing constructor and create our own constructor, or sorry, define our own constructor that sets the properties that we want. So just like how I mentioned, each each node has pointers to a left child and a right child. So initially when we create a node, we just want to set each of those to null. Um, oh, do you have to put in the object? No, you don't have to. Okay, and also it needs to have its own value. So that'll just be, so we're gonna assume that L is a list, and so we'll just add the first value um, here to our topmost node, and then we're going to um, add each of the consecutive values in the list using an insert method that we're going to define. So this L prime will just be our list L, just without the first element. And so we're going to iterate over this list L prime, and for now we'll just leave this commented, but we're going to define a insert method that once we have like our root node or our first node, we can just go ahead and insert more elements, more nodes. So let's go ahead and define a insert function. So remember that we had those conditions on our binary search tree that the left side, the left tree of a node must be less than the value of the parent node, and the right side, right tree must be greater than the value of the parent node. So given a node v for insertion, we just want to see, is this less than or equal to um, our value, and if so, then we want to insert it into our left tree. So we'll check first if a left tree exists at all. So actually, to better visualize this, let's see. So let me just pull up a example here. So say if we have a node such as 5, and say we also have on its right side a node 10. Now if we want to insert a node 3 here, then first we'll check our node 5, and we'll see, okay, is 3 less than 5? Yes. Okay, at that point we'll check, does our node 5 have a left tree? In this case we don't. So in that case we can just simply go ahead and say if self.left equals null, then self.left equals bst v. So here we just call the constructor again because the constructor automatically creates each node for us, and also creates an empty left and right subtree each time. So instead of just saying left equals v, where v is just an integer, calling this constructor here actually creates a node with that integer v. So that's the case where a left tree doesn't exist. However, there could also be a case where we already have a left subtree. So say we're in this situation where we already have a left subtree, and now we want to add another element that's smaller than 5. So for example 1. In that case, we would actually want to call this insert function recursively. So we'd want to do something like this. So self.left and call the insert function from our left node. So what this does is, so it'll recursively call this function, at which point we're looking at everything from the perspective of our left node, for example 3. So we compare, is 1 less than 3? It is not. So then again, according to this logic, we will check our left tree. In this case, it doesn't exist, so we'll create a left tree. And you can see that the node 1 was inserted. Right, now, likewise, we want to do the same thing for our right node. So if the value we're trying to insert is greater than the value of our current node, then we can just do the same thing. So if self.right, check if the right tree is empty. If it is, just go ahead and create it by recursively calling the constructor. And if it does exist already, then we can just go ahead and recursively call the insert method on our right tree. So now an example of this would be, if we want to add 12 to this tree here, then in that case we'll first check node 5. 12 is greater than 5, so then we check to see if our right tree exists. So it does exist, which is node 10. So we check if 12 is greater than 10, in which case it is. We check if 10 has a right subtree. It does not. So we go ahead and add 12 as the right child of node 10. And essentially 12 becomes this right tree for node 10. Okay, so now we can go ahead and uncomment this method, that line that we commented earlier. So that was the insert function. So now next we'll go ahead and define a search function, because after all, this data structure is called a binary search tree, and it's supposed to help us with um, searching for values. So yeah, in computer science, this is a data structure used for searching, and it's much more efficient than just iteratively searching through a list, because in a list you could potentially have to check for every element in this list, whereas with a binary search tree, you can avoid searching for you can avoid doing that, because we just have like these properties where um, the value you're searching for is less than your top node. So if it's less than 8, then you can just ignore all the elements on the right in the right tree, and that saves you a lot of computation time. I hope everything makes sense so far. If not, please feel free to ask. So let's go ahead and implement these this search function. So we're searching for the value v. So we'll start at the top. So if self dot value, sorry, if v equals self dot value, turn true. Oh, so we have a question here. So what does object do? Uh, right, so every class uh, in Python automatically inherits from the object class. In this example, we just wanted to make that explicit. And so we explicitly specified this inheritance. Hope that makes sense. So let's continue with our search function. So if it doesn't match with the first node, then we'll have to go ahead and recursively call the search function on either the left or right subtree. So before we do that, let's check if those trees exist, first of all. So if self.left equals, so if we don't have a right tree, if we don't have a left tree, then we can just go ahead and return false. For now, we'll just store that in a variable. We'll return it later. Else, if it does exist, then we can call our left. We can call the search function on our left tree recursively. So self.left.search v, and we'll store the output or the result of that recursion in the value lval. Likewise, we also want to check our right side. So self.right equals null. And likewise, if we do have a right subtree, then we can recursively call our search function on our right tree. And at the end, we can just return lval or rval. If either of those are true, then that that node exists in our tree. We have another question here. Let's see. So, does every class have a init definition to initialize variables so they can be used in later methods? Yeah. So by default, every class automatically has an init method. However, you can override it to create your own. Alright, so we have we defined a search function. So now, let's see, what else should we implement? Okay, so next, another thing that we might want to find using, or another thing we might want to find about our binary search tree is what's its maximum depth. So, the maximum depth here. So, for example, this tree here has a depth of 3 on each side. So let's add another node to it. So if we add the node 0, now our tree has a maximum depth of 4. We want to write a function that returns this value to us. So let's define a function called max depth. So if self.left equals null. So again, we're just checking to see if our left and right subtrees exist. So if the left side is null, we'll just store our lval depth as 0. Else, we can go ahead and recursively call our max depth function on our left tree. So so again, storing our output from our recursion in lval, so self.left.search v. Oh, sorry, not search, my bad. Max depth and +1. +1 because we know that a left tree exists, so we can just count that as our first depth. Or sorry, count the current node as our first depth, and then recursively call this this method here to go ahead and go further down the tree to see how deep it really goes. So again, whatever we do with the left side, we also must do with the right side. So check if a right tree exists, rval equals, if it doesn't, rval equals 0, else recursion and then at the end we just simply want to return the bigger value between lval and rval. because if we go back to our example here, if that method was called on this binary search tree, it would, go down this path and return 4, and it would go down this path and return 3. And then it would just take the max of 4 and 3, which is 4, and it would return that the max depth of this tree is 4. Okay, so it looks like um, that's it. Um, Also, optionally, if you wanted, um, there's no easy way to like print a binary search tree, but I'll leave this as an exercise to you. If you wanted, you could, um, overwrite the str function, which is part of every object by default. You can override it. Um, so this str method, it basically just is a string representation of your object. So um, if you wanted to, print your binary search tree in a very pretty way, um, so I'll leave this as an exercise to you guys. But you could write a method that prints your prints something like this. But we don't have the time for that in this tutorial, so I'll just leave that as an exercise. Okay, so let's go ahead and run this just to make sure we don't have any syntax errors. Oh, we do. Okay, so we missed a semicolon. Let's fix that and run it again. Okay, looks like we're good. Um, Alright, so let's go ahead and create a binary search tree. So you can just call BST, the BST constructor, pass it a list. So that'll be, let's pass in 5, 3, 7. Essentially this tree that I copy pasted here. So 5, 3, 7, 8, 2, 4, 7, 14, 7, 25, 9, 1. And actually here I have uh, I just have this string method that was provided to me by the prof. Um, it uh, it returns a string representation of this tree, but it's just not very um, friendly to read. But just to have some sort of output, we'll use that. Let's go ahead and run this. Oh, I need to run this again. There we go. So you can sort of see here 5, we start with a node 5. On the left side we have 3, 2, 1. As you can see here in this representation we have 5, 3, 2, 1 all on the left side. And then later on it starts printing the right side of our tree. So 7, and 7 has 2 other 7s in its left tree. and so on. Let's run some uh, more. Let's try to run our search methods. So we have X. So let's search for 5 in our tree. Okay, so as expected, 5 exists in our tree. And let's search for 13. Yep, our search function works. And let's just test our insert and then search for 13. So, okay, there we go. We've also tested our insert method. So yeah, so there you go, guys. That was a tutorial on binary search trees and how to implement binary search trees in Python. Let me just look over my notes here to see that I didn't miss anything or I need to mention anything else. Yes, let's also print the depth of our tree. So x dot max depth 4. Yes. Yes, this will be posted later. This will be uploaded. Okay. So that's it for the code. Oh yeah, let's just, I guess, go back to our visualization to see um, what the creation of this tree looks like. So let's go ahead and add our first node, which was 5. Then we added. So I'm just going over this list here. This list that we passed in earlier to create a sample binary search tree. So we add 3, and we can add 7, we can add 8, add 2, we can add 4, we can add another 7, we can add 14, we can add 25, we can add 9, and we can add 1. Did I miss something? 8, 2, 4, 7, 14. Oh, and I think I missed a 7. So there we go. So yeah, there you have it. Just a visualization of what the building of a binary search tree looks like. Um, so yeah, that's pretty much it for this tutorial. We have a couple more minutes left, so I'll just stick around for any questions you guys might have. And so yeah, thanks for attending this tutorial. And yeah, stay healthy and stay safe.